What if the largest planet in our solar system had been keeping a secret for billions of years? A secret so unexpected that it forced scientists to question everything they believed about how giant planets form. One spacecraft took an enormous risk. It traveled billions of kilometers, survived radiation levels that should have destroyed it, and flew closer to Jupiter than any probe before it. What it discovered changed our understanding of the solar system and opened new questions about worlds beyond our own. This is the story of the Juno mission. On the 5th of August 2011, a powerful Atlas V rocket lifted off from Cape Canaveral. On board was Juno, a spacecraft unlike any that had gone to Jupiter before. It could not fly straight to its destination. The distance was too great, and the spacecraft too heavy for the rockets of that time. Instead, engineers designed a long, clever path. Juno first headed into deep space, then swung back toward Earth. On the 9th of October 2013, it flew past our planet and used Earth gravity like a slingshot. This single maneuver added more than 14,000 kilometers per hour to its speed without using extra fuel. After nearly 5 years and almost 3 billion kilometers of travel, Juno finally reached Jupiter. On the 4th of July 2016, the spacecraft performed one of the most dangerous maneuvers in space exploration. To enter orbit, it had to fire its main engine for 30 minutes while passing through Jupiter deadly radiation belts. Any failure would have ended the mission instantly. The engine worked. Juno slipped into a long, looping polar orbit. Its closest approach brought it only 4,200 kilometers above the cloud tops. Its farthest point stretched more than 8 million kilometers away. Each full orbit took 53 days. Scientists had serious doubts about how long Juno could survive. Jupiter radiation belts are among the harshest environments in the solar system. Earlier spacecraft had suffered major damage from them. Juno was protected by a thick titanium vault around its most sensitive electronics, but no one expected it to last much beyond its original 20-month plan. Yet something surprising happened. The spacecraft found and followed a narrow path where radiation levels were 10 times lower than predicted. This unexpected safe corridor gave Juno years of extra life that no one had planned for. The first images Juno sent back stunned the team. At the poles, Jupiter looked nothing like the familiar banded planets seen from Earth. Instead of smooth stripes, there were clusters of giant swirling storms. Some of these cyclones were larger than Earth itself. They circled the poles in stable patterns that no model had predicted. The northern pole showed 8 distinct vortices. The southern pole had 5. These structures remained remarkably steady from one orbit to the next. For the first time, scientists saw Jupiter as a world of organized chaos at its highest latitudes. The planet was far more dynamic and strange than anyone had imagined. Juno carried 9 scientific instruments, but its most powerful tool was its orbit itself. By flying so close to the planet on every pass, the spacecraft could measure tiny changes in Jupiter gravity. These measurements were so precise that scientists could detect speed variations as small as 1/100th of a millimeter per second from more than 600 million kilometers away. Each close pass gave new clues about how mass was distributed deep inside the planet. The real investigation was only beginning. What Juno would uncover next would challenge decades of accepted theory about the largest world in our solar system. With every close pass, Juno kept gathering new evidence about what lay hidden deep inside Jupiter. The spacecraft sent a constant radio signal back to Earth. Scientists tracked the tiniest changes in that signal caused by the planet gravity tugging on the probe. These changes were incredibly small, sometimes less than 1/100th of a millimeter per second. Yet they were enough to build the most detailed map of Jupiter interior ever created. It was as if the planet itself was whispering its secrets across hundreds of millions of kilometers. For decades, researchers had argued about Jupiter core. One group believed the planet had a solid rocky center made of heavy elements. Another group thought there was no core at all, and Jupiter was made of the same hydrogen and helium mixture from the center all the way out. Both ideas fit the limited data from earlier flybys. Both had strong supporters. Neither could be proven right or wrong until something got much closer and stayed longer. Juno became that something. The gravity measurements told a completely different story. Jupiter did have a core, but it was nothing like the solid ball scientists had imagined. Instead, the core was diffuse and spread out over an enormous region. Heavy materials were mixed with the lighter hydrogen and helium gases. There was no sharp line separating the core from the outer layers. The boundary was gradual and blurry. This strange core reached almost halfway from the center of the planet toward the cloud tops. To understand what this meant, imagine a sugar cube slowly dissolving in a glass of water that is being stirred very gently. At first, the cube is solid and easy to see. As time passes, it breaks apart and creates a zone where the sweetness slowly fades into the surrounding water. There is no clear edge anymore. Juno showed that Jupiter core behaves something like this. It is a fuzzy mixture rather than a neat solid ball sitting at the center. This discovery created serious problems for the accepted theory of how giant planets form. According to that theory, a solid core had to form first in the cold outer parts of the young solar system. Once it grew large enough, its gravity could pull in huge amounts of hydrogen and helium gas. Without a solid starting point, the whole process should not work. Yet Juno data suggested Jupiter core was mixed and spread out. Either the core had started solid and then slowly dissolved over billions of years, or the formation process itself was more complicated than anyone had thought. Some researchers wondered whether a giant collision early in Jupiter history could have broken apart an original core and mixed the pieces throughout a large region. Computer simulations were run to test this idea. The results were mixed. A big impact could disrupt the core, but the heavy materials tended to sink back down and reform a clearer boundary. The models did not easily produce the fuzzy core Juno had found. This meant either the mixing happened through some slower process, still not fully understood, or the entire picture of gas giant formation needed to be rebuilt from the ground up. The gravity data kept improving with every orbit. The picture became clearer and more surprising. Jupiter was not a simple layered world with distinct zones like the old textbooks described. It was a planet with a complicated and still active interior. Heavy elements were not neatly concentrated at the center. They were distributed in ways that suggested ongoing movement and mixing deep below the clouds. For the first time, scientists had real evidence that the largest planet in our solar system was still evolving inside, long after it formed. While the team worked to understand these gravity results, another group of instruments began sending back equally unexpected information from higher up. The atmosphere itself was behaving in ways no model had predicted. What Juno found there would prove just as surprising as the strange core hidden deep below. While the gravity data revealed the strange fuzzy core deep inside Jupiter, another instrument began exploring the layers just below the visible clouds. Juno carried a specially designed microwave radiometer that could peer hundreds of kilometers beneath the ammonia cloud tops. What it found showed that the atmosphere was far more active and complicated than anyone had expected. One of the first surprises was the distribution of ammonia. Scientists had assumed this gas would be mixed fairly evenly throughout the upper atmosphere, or at least follow the familiar banded patterns seen from Earth. Instead, Juno discovered a massive concentrated plume of ammonia circling the equator. This plume extended downward more than 350 kilometers from the cloud tops. It was as if a huge river of ammonia was rising from deep inside the planet and spreading out only near the equator. This vertical movement suggested powerful circulation patterns that reached much deeper than any previous model had predicted. Even more dramatic was what Juno learned about the Great Red Spot. This giant storm has raged for at least 400 years and is large enough to swallow Earth several times over. Earlier observations showed it as a high, swirling cloud feature, but no one knew how deep it went. Juno measured the storm from above using both gravity and temperature data. The results were astonishing. The roots of the Great Red Spot extend at least 300 kilometers below the visible clouds. In some measurements, the structure reached even deeper. The storm is not just a surface phenomenon. It is a deep-rooted vortex that affects enormous volumes of Jupiter atmosphere. Temperature readings showed the spot is cooler than its surroundings at higher levels, but warmer deeper down, suggesting that internal heat helps keep this ancient storm alive. At the poles, Juno revealed another completely unexpected world. Instead of smooth or chaotic clouds, the spacecraft found organized groups of giant cyclones. 8 distinct vortices circled the North Pole, and 5 surrounded the South Pole. Each storm was roughly the size of Earth or larger. These polar cyclones remained remarkably stable over many orbits. They did not drift apart or merge randomly, as simple models suggested they should. Scientists began calling them polar vortex cities because of their organized and persistent structure. No one had predicted that gas giant planets could maintain such regular and long-lasting storm systems at their poles. Perhaps the strangest atmospheric discovery involved lightning and a new type of precipitation. Earlier missions had detected lightning on Jupiter, but scientists assumed it came from deep water clouds far below the visible layers. Juno found flashes occurring at much higher altitudes, where temperatures are far too cold for ordinary water clouds to exist. Further analysis showed that these high-altitude storms involve a strange mixture of water and ammonia. The mixture stays liquid even in extreme cold and forms slushy hail like particles. Researchers named them mushballs. These unusual hailstones fall through the atmosphere carrying ammonia and water between different layers. The process helps explain both the strange lightning and the uneven distribution of ammonia that Juno had already mapped. All of these findings painted a picture of an atmosphere that is constantly moving and mixing on a massive scale. The belts and zones visible from Earth are only the top layer of much deeper circulation. Winds and storms extend hundreds of kilometers down. Materials are transported vertically in ways that connect the upper clouds to regions far below. Juno showed that Jupiter weather is not a shallow surface show. It is a deep dynamic system that reaches into the planet interior. Each new discovery raised fresh questions. How do these deep circulation patterns stay stable for so long? What powers the organized polar cyclones? How does the fuzzy core influence the atmosphere above it? The investigation was uncovering more mysteries than answers. And while the team worked to understand the atmosphere and interior, Juno began studying something even more powerful and puzzling. Jupiter's magnetic field was about to reveal its own set of surprises. Juno next turned its attention to one of Jupiter's most powerful and mysterious features. The planet's magnetic field is the strongest in the solar system. It stretches millions of kilometers into space and creates a vast magnetosphere that can even reach as far as Saturn orbit. Scientists expected this field to behave in a relatively simple and orderly way. Instead, Juno revealed a magnetic environment full of complexity and surprises. The spacecraft carried a sensitive magnetometer mounted at the end of one of its long solar panels. As Juno flew close to the planet on each orbit, it mapped the magnetic field in extraordinary detail. The data showed that Jupiter's field is not symmetric. It is noticeably stronger in the northern hemisphere than in the southern. There are intense localized patches, and the overall structure changes over time. One of the most striking features is a region of extremely strong magnetic field near the equator known as the Great Blue Spot. This spot is not visible in ordinary light, but stands out clearly in magnetic measurements. Even more surprising, the Great Blue Spot is slowly moving. It drifts eastward at a few centimeters per second. At that rate, it would take roughly 350 years to travel all the way around the planet. Jupiter's magnetic field is not fixed. It evolves. These findings challenged long-standing ideas about how planetary magnetic fields are generated. On Earth, the field is produced by the movement of liquid iron in the outer core. On Jupiter, scientists believe the field came from a deep layer of liquid metallic hydrogen, where extreme pressure turns hydrogen into a conductor. Juno data suggested the process is more complicated. The fuzzy core and regions of partial stability inside the planet appear to influence how the magnetic field forms and changes. Some layers may act like filters, allowing only certain parts of the field to reach the surface. This helps explain why the field looks so irregular and why it changes with time. Juno also provided new insights into Jupiter's spectacular auroras. These northern and southern lights are hundreds of times more powerful than Earth auroras, and they burn continuously. Earlier observations showed bright ovals around the poles, but Juno flew directly through the regions where the auroras are generated. The spacecraft measured the energy flowing into the upper atmosphere and found that much of it comes from Jupiter's own rapid rotation, rather than from the solar wind. The planet spins once every 10 hours, and this fast rotation helps drive electric currents that light up the sky. The auroras are also strongly affected by Jupiter moons, especially Io. Volcanic material from Io feeds into the magnetosphere and creates bright spots and tails in the auroral displays. Juno even captured images showing how these moon-induced features move and change. The magnetic field measurements added another layer to the growing mystery of Jupiter's interior. The same fuzzy core that explained the gravity data also seemed connected to the strange behavior of the magnetic field. Stable layers deep inside the planet may be shaping and filtering the dynamo that generates the field. What scientists had once pictured as a clean, simple process turned out to involve multiple interacting regions with different properties. The more Juno measured, the more it became clear that Jupiter is a world of layered complexity rather than simple zones. By this point in the mission, the spacecraft had already survived far longer than planned and had delivered far more surprises than anyone expected. Yet the investigation was not finished. Juno orbit was slowly changing, and the spacecraft began making close passes by Jupiter's largest moons. What it found there would add an entirely new chapter to the story of the Jovian system. By the time Juno completed its original mission plan, the spacecraft was still in excellent condition. Radiation damage had been far less severe than expected, and all major instruments continued to return high-quality data. NASA decided to extend the mission. Juno began a new phase focused not only on Jupiter itself, but also on its largest moons. The spacecraft orbit was adjusted through a series of gravity assists, and it started making close flybys of Ganymede, Europa, and Io. On the 7th of June 2021, Juno passed just 1,000 kilometers above the surface of Ganymede, the largest moon in the solar system. The images sent back were the most detailed ever taken of this icy world. They showed a complex surface with bright and dark regions, long linear features, and many impact craters. Some of these linear grooves may be signs of past tectonic activity driven by internal heat. During the same flyby, scientists also used data from other telescopes to study Ganymede's thin atmosphere. To their surprise, it contained more water vapor than expected. This finding suggested that water vapor could be more common in the atmospheres of icy moons than previously thought. 2 years later, on the 29th of September 2022, Juno flew past Europa at a distance of only 350 kilometers. The images revealed a heavily fractured icy surface with long ridges, troughs, and dark patches. Some of these features may indicate that material from below the ice occasionally reaches the surface. Europa is believed to have a vast salty ocean beneath its icy shell, and these close observations gave scientists new clues about how that ocean interacts with the outer crust. The flyby also helped refine models of Europa ice shell thickness and its potential for geological activity. The most dramatic encounters came with Io, the most volcanically active body in the solar system. In 2023 and 2024, Juno made several very close passes by this fiery moon. The spacecraft captured the first high-resolution images of Io northern latitudes and discovered previously unknown mountains. One striking peak was named Steeple Mountain because of its sharp cathedral-like shape. Juno also observed massive volcanic eruptions and tall plumes of gas and dust rising high above the surface. One of the most impressive features was Loki Patera, a huge lava lake more than 200 kilometers across. The smooth, glassy reflections seen on its surface suggested that parts of Io are constantly being resurfaced by fresh lava flows. On one particularly active day, Juno recorded multiple large eruptions happening across a wide region of the Moon. The energy released was among the most powerful volcanic events ever observed anywhere in the solar system. Throughout these Moon encounters, Juno continued studying Jupiter itself. Its microwave instruments provided new estimates of water abundance in the planet atmosphere. The data showed higher concentrations of water-related materials near the equator than in other regions. This uneven distribution gives important clues about how Jupiter formed and how materials were delivered to it during the early history of the solar system. Even after more than 8 years at Jupiter, the spacecraft remained operational. The mission had been extended multiple times because Juno kept delivering valuable and unexpected results. By 2026, the probe was still sending back new information about the planet, its magnetic field, its atmosphere, and its moons. What began as a mission to study Jupiter's interior had grown into a much broader exploration of the entire Jovian system. Juno showed that Jupiter is not a simple gas giant with clear layers and predictable behavior. It is a world with a fuzzy, mixed-core, deep atmospheric circulation, powerful and changing magnetic fields, organized polar storms, strange forms of lightning, and active moons that continue to surprise scientists. Every new piece of data raised fresh questions about how this giant planet formed, evolved, and continues to change today. The mission did not answer every mystery, but it fundamentally changed what we thought we knew about the largest planet in our solar system and about how such worlds behave across the universe. If you enjoy discovering surprising facts and stories about space science and the natural world, subscribe to the channel. There are many more fascinating investigations and unexpected discoveries waiting to be explored in future videos.